Hello, hello everybody. I'm Alexandre Lecorneur from SUEZ. I'm a hydraulic engineer.
And I'm Pedro Fonseca, head of the hydraulic department at SUEZ.
Okay, and we will tell you about how we use Wolfram System Modeler to optimize our pipes and pumps because we do design and build water plants, wastewater plant as well as drinking water plants and desalination plants. So we do have a lot of pipes and pumps and water tanks to design. Okay, so we'll take a simple case. We will have a low tank that is receiving a flow coming from a sewage network, so wastewater flow, very variable, of course. And we want to bring it to a wastewater plant which is located higher. But we don't want to bring the whole flow there. We want to bring up to 2.2 cubic meter per second. And the excess flow, which happens usually during rain, we will send it to another treatment, which is a bit lower. For this, obviously, we need some pumps to lift the water. We need some pipe. We need a pipe network. You see, we made here a long pipe, 2.5 kilometer, and some short pipes here. And we need something here. Uh, we don't want most of the time we want these circuits to be closed. Only when there is the rain peak flow, we have water flowing through this circuit. So we need a control valve. At this stage, it looks obviously like a Modelica system modeler diagram, and it is eventually. At this stage, it's not real pumps, not real valves, it's just ideal flow sources. Okay, so we have, I would say, a kind of architecture, but not a design yet. And Pedro will tell you more.
So with these simulations, we can address one of the most critical design decisions in water conveyance, that is the selection of optimal pipe diameter, pumps, etc. And this decision is inherently multi-objective because, well, it's a balance of competing criteria like hydraulic performance, construction costs, environmental footprint. For instance, in hydraulic performance, if pipes are undersized, well, head losses increase, discharge pressure at the pumps rises, energy consumption grows. On the construction costs, well, on this particular project, part of the pipeline will be built using microtunneling, as we can see on the picture above, yes, which has a very high unit cost, yes. And on an environmental footprint, well, certain sections cross sensitive or complex areas, which increases both construction costs um, and CO2 emissions by consequence, yes. So all these variables, together with the minimum velocity constraint required to ensure transport of settable solids, become part of the optimization vector used to determine the most suitable pipe diameter, yes. Now the key input is the flow distribution over time. We can see on the left side. The system operates most of the year at low flow rate, occasionally medium flow, only a few days per year, peak flow. Well, designing the system to be optimal only for peak flow, well, obviously leads to inefficient solution for most of the operation conditions. And so our goal is therefore to find pipe diameter that optimizes total life cycle cost, emissions, and for the main operation condition regime. On the next slide, so talking about multiple objective optimization with system modeler. To select the optimal diameter, considering all these inputs, we use system model coupled with Mathematica. The model includes a time-dependent flow table that we already saw it there as an object, which represents the long-term flow distribution. Yes, this flow profile fits both the pumps and the control valve that was mentioned previously. We then load the simulation into Mathematica to run the model thousands of times using an automated optimization workflow. The objective function minimizes TOTEX, and this includes CAPEX, well, construction costs, OPEX, operational costs in mostly energy consumption, and CO2 footprint. Yes. So this is a multi-objective optimization problem solved through parametric sweeps and search algorithms that converge towards kind of a Pareto optimal solution. The resulting optimal design is well, it's kind of obvious and at the same time interesting. The long microtunneling pipeline on this example converges to a small diameter because of the construction costs. And on the other sections, the lower differential cost converges to a larger diameter to reduce energy consumption. Yes, and so it kind of finds the balance on a expected way on this example. Moving forward.
Okay, so now we have a pipe network with diameters. So we know the total head we need on the pumps, well, the discharge pressure, because we have the networks, and we typically receive several offers from pump manufacturers, and we have to select a pump model. The manufacturers typically they send us this type of curves. The first one is showing the flow, the total head, the pressure versus the flow. There are efficiency curves. All these curves are at nominal rotation speed for the pump, and quite often, most of the time, we operate this pump at variable speed. So we have the possibility with System Modeler and our library to operate this pump at variable speed, and there are some rules to modify this curve according to the speed. And we can do a very simple model with the pump model. First we run one pump from 0 RPM to max RPM. We reach something like 6,000 cubic meter per hour. This is the flow. And this is the efficiency, meaning it's the ratio between the shaft power we inject in the pump and the hydraulic power that is restricted to the system. So the efficiency at the beginning is not good. This is a good zone, 0.8 and even higher, and this is not a great zone. With two pumps, we get a higher flow, and the efficiency curve is like that. But here we'd better switch to 3 pumps. And here we'd better switch to 4 pumps, because we want to stay always on the best possible efficiency to spend as less electricity as possible. So with a simple simulation, we can get a quick overview of what we could get this dashed line with this pump model, and we can easily compare different models. That's very simple and very efficient. So now we have a pump model. It's quite okay. We are quite happy with this efficiency.
So, well, after selecting pumps and pipe diameters, it is typical to perform transient analysis on the system. So we kind of simulated critical scenario, typically all pumps running at full speed and a sudden stop due to power failure. For the purpose of this presentation, we use a simplified rigid column model, not an elastic pipe behavior. But we do include pump inertia, motor inertia, behavior. Well, the pump at a given moment becomes a dissipative element after shutdown. The results, well, we can see it on the screen. The results show that immediately after power loss, pressure downstream the pumps, that is at that pipe's signal in red, drops rapidly from 6 bars approximately to subatmospheric pressure. This occurs because, well, the 2.5 kilometers of water column that is going forward along the pipeline has a strong inertia. And so water continues moving while the stop pumps becomes a restriction in the system, yes. This can lead to a pipe collapse. Unfortunately, it does happen. Pipelines are quite robust against pressure from inside to out, but well, when we submit it to negative pressure, it's quite easier to implode them. Yes, and so this is a major risk that we must mitigate. Yes. On next slide, so we can see that we added a vessel on top of the model, a pressure vessel. So this vessel acts as a reservoir with compressed air inside, acting as a cushion, and so it provides flexibility during the shutdown. When power drops and pumps rapidly lose their ability to supply flow, the vessel temporarily supplies water to the network. Yes, the expanding air maintains pressure within safe limits. We can see on the plots that around 600 seconds, we clearly observe the transition between pump supply to vessel supply. And so we can see that the pump supply rapidly drops at the exact moment where the vessel starts supplying water to the system. Yes. At the same time, we can see the air expansion progressively reduces pressure on flow, but this is controlled on a gradual manner. So we can see the flow rate going down slowly, yes, avoiding a sudden depressurization of the system, yes. The vessel behavior on the first plot can be, well, we can see that the liquid level decreases as water is supplied, yes, and then the system reverses and the vessel refills again. Well, this is a cyclic movement after the pump stop. We can also observe that the vessel is correctly sized because we can see that the vessel never empties. Well, it's represented by the orange zero line, yes, there. And at the same time, on the lower plot, where that is representing what we were seeing on the previous slide, we can see that now pressure no longer goes to subatmospheric pressure; it remains above zero. Yes, well, with this hydraulic design completed, we then move to the control architecture, and that will be Alexandre continuing.
Thank you, Pedro. So to complete our system, obviously we need a control, and for this system, the basic thing, we want to keep the low tank at more or less constant level. We don't want it to overflow on the roads, and we don't want it to be drained because we cannot pump anymore. So quite logically, we have a level set point for this tank. We have a level measure, and we feed a PI controller that accelerate or slow down the pump. You can see on this diagram that we do not have the 4 pumps of our system, but in fact we have some flow division and flow multipliers, and we can send to these components a value which can be 1, 2, 3, or 4. If it's 4, it's like a pumping station with 4 pumps, in fact. But we simulate only 1 pump to have a lighter simulation for a very similar results. This block is in fact just starting another pump or stopping a pump depending on the speed of the pump in operation. And very quickly we can see the reaction of the system over a quite long period, and we can simulate 20 days very quickly in 1 minute. I can show actually just at the end of the presentation during the question the real simulation, and we can quickly identify issues. Here we have an issue. We have multiple start and stop of the pumps within a very short time, and we don't like that at all. And it's very easy to understand, analyze, and to solve these issues. If I had been on site, I would need to stay on site several days to see the issue happening. Then I would try another setting. I would need to stay again several days to check if the result is okay. So there's obviously a strong interest for us to use this tool. And things we do also, still with Mathematica, we can do also automatic optimization of control parameters. With Mathematica, we give a target to Mathematica for a variable. It could typically be amplitudes of oscillation to minimize, or overshoots, or number of start and stop of pumps, etc., or a composite variable that takes into account all these factors. So that's part of the things we do with System Modeler, and we can really, we started something like 2 years ago with little things, and now we can really use it on real cases, and with great benefits. Okay, that's the end of our presentation. If you have any question, we can answer, of course. And
Yes. Thank you, Alexandre and Pedro. It was a very informative talk. So if I understand correctly, you created the library from scratch, right?
Yes, correct. Yes.
So I have the same question for you as I had for Martin. What key principles did you follow in your library development journey?
How to answer this question? We tried to use Modelica standard libraries for 2 or 3 days, and with no knowledge at all of Modelica. And after 3 or 4 days, I was nowhere. I couldn't do anything with the fluid library of Modelica. I could do things with the electrical library, which I do understand. Well, not all, but so after 4 days, I started to create my own library with small things. It did work. Not great, but we could simulate an interesting project. And that was the beginning. And then we developed more and more components. At some points, the library was a big mess, so we had to restructure it. So and we are still working a lot on this library to make it more stable, to make it more user-friendly. It's a continuous work.
Right. Can I comment on that? I think what you said here is so we see here the fluid library, same as Martin, is that it's an advanced library. Then there are the rest of the, say, MSL libraries are typically much easier to use than the fluid library. But that comes from fluid systems having so many ways of wanting to do stuff in many times. So I'm sure if we compare your library with Martin's library, they're quite different because you have different needs.
Sure.
And I think that's part of it. And you're also showing there, saying there that what you did is you started with some simple model of something, and then it evolved from there. And I think that's a very common way of how you actually do, because then you really learn from the basics, from the ground up, and and then at some point you come to the decision, now it's actually time to break this down and do it really nicely, well structured, and get a library that is perfect for our needs.
Right. We have a question from Martin. What variables did you use for the interface in your library, like in the connectors?
So at the interface, our we call it head library. We use total head in meter, which is kind of pressure, but expressed in meter of water column. It's the level of the water in a transparent tube that would be connected to the pipe. So it's the altimetry of the water in the pipe or the reservoir. And actually, we did use the volume flow, not the mass flow. It's not correct at all in terms of physics, but for our applications, that's what we use, and that's really fine. So, and also we have another library where we use streams also for process things with suspended solids, salinity, etc. And we have some more components with that you on this library actually. That's basically
that was a really good example, by the way, of you and of the thing of you have so different viewpoints on the same thing. For you, it makes sense to have meters. For Martin, for sure, it doesn't. When his when his vehicle goes uphill, meters would not be very good.
Okay, so I have a follow-up question for Martin as well. What about the media model you guys are using in this library? Do you use any media model?
No, we don't use any media model actually, because when I developed it, I really had difficulties to understand how this media model was working. So I made it's basically water that we use in water industry. So it's water. We can adjust salinities, temperature. The viscosities are of course updated according to these, and the volumic mass are updated according to these properties. And I would say that's fine for what we do. So our media is water. But yeah, basically yes. We use gas a little bit, but on specific cases.
Right. So there was a question from Andrew. Did you say that you could troubleshoot by matching plots to failed components in the system model? If so, is there a machine learning technique to match curve forms from real sensors to system simulations?
We did not try that at all yet. It would be interesting actually. These days, I would say we are designing plants with these systems. These plants will be built, but it always takes time. It takes several years for this project to be built and commissioned. And in a few years, it will be very interesting to compare if what we did during engineering phase does match the reality of the site and recalibrate things. But at that stage, we did not do that yet.
Right. And which criteria did you use to place your surge tank on the right of the pipes or to the left?
Well, we want this. Pedro, maybe you can answer this question.
Yeah, I was writing it. Yeah, I was typing it right now. I mean, the location, if you mean the location, it's common engineering knowledge from water hammer transient analysis that we should continue the supply of water the closest possible of the point where there has been a shortage of water. So in this sense, it's to approach the vessel to the pumps that are the element that change their condition upon power failure. If we place it further away, we are going to have the phenomena developing until it finds the vessel, and so we end up with two oscillation systems, one upstream the vessel and another one downstream the vessel. I don't know if this was the question.
Right. Right. Thank you, Pedro. You seem to use the integration between system modeler and Wolfram language quite heavily. Could you elaborate a bit on how that integration has been helpful? I know you mentioned optimization, but in general, how has the integration been helpful in your workflows?
You want to answer this question, Pedro?
Yeah, sure. So we often develop a model that can be later on seen as a black box to the user, or let's say to the end user, and then the end user explores it with Mathematica. It can go from simple swap of parameters, multiple parameters, until there's an optimum or a failure case that is found, or we can actually implement some more sophisticated, let's say, optimization algorithms to calibrate the outcomes to a existing curve, for instance. It's one of the answers I gave to the question: do we couple it with real data from site? Well, it's easy to couple it with real data from site by using Mathematica as the intermediate actor, trying to, let's say, optimize parameters until we get an answer similar to the site. Yes, it brings flexibility to the workflow, basically.